In this lesson, we want to use our epsilon-delta limit definition to prove limits involving quadratic functions. So let's start out with this example. We want to use our epsilon-delta limit definition to prove that the limit as x approaches 2 of x squared plus x plus 1 equals 7. Notice if we put 2 in here for x, we get 4 plus 2 plus 1, and that is 7. So what we want to do, recalling our epsilon-delta limit definition, we assume that epsilon greater than 0 is given, and we need to find a delta. This will be some function of epsilon greater than 0, such that f of x minus L in absolute value is less than epsilon whenever x minus c in absolute value is less than delta, and greater than 0, but this part won't come into play. So recalling how we did this for linear functions, we start out with the same thing. We begin with the f of x minus L in absolute value part, and we'll try to algebraically manipulate it until we see a x minus c come out somewhere. And keep in mind our c is 2 in this case. So we want to take this and manipulate it until we see an x minus 2 coming out somewhere, and then move everything over to the other side, and then we'll be able to pick off what our delta should equal. So let's start out with, now we're not going to set this less than epsilon right now. Notice that, or recall that when we did our limits for linear functions, we set this less than epsilon and we began manipulating. Before we set it less than epsilon, we need to manipulate it first a little bit. So let's put in our x squared plus x plus 1. That's our function f of x, and our L is 7. And now we're going to manipulate this a little bit first. So notice that this is, and notice that that factors as, alright, now we see here, right here is our x minus c. So this part we want to keep. And what we want to do here now is we want to set this less than epsilon. And it would be great if we could divide this to the other side. However, we can't do that because our delta cannot be dependent on x. If we were just to divide this to the other side, then our delta would be dependent on epsilon and x, and that can't be true, or that can't be. Our delta can only be dependent on epsilon. If you recall for the linear proofs, what we ended up here was with a number like, one time we ended up with a 4, and then we just divided it to the other side, and we said delta was epsilon over 4. But we can't do that in this case, because it's not a number, it's a function of x. So we're going to have to do a little more manipulation here, and so here's what we're going to do. We need to get rid of this term right here, the x plus 3. So we're going to do this. We're going to say from now on, we're always going to assume, that the delta is always chosen less than or equal to 1. In which case then, x minus 2 will always be less than 1 because we always set this less than our delta. And this is the same as, this is equivalent to saying that x has to be between 3 and 1. Notice that this is the same here as x minus 2 less than 1 greater than negative 1, and if we add 2 to everything, we end up with this. Now what this is going to do is going to allow us to find a bound on the x plus 3. So if we assume our delta is always going to be chosen less than 1, no matter what epsilon is picked to be, now this implies then that, therefore, the x plus 3 times x minus 2, well, that's going to be less than, what's the biggest that x plus 3 could possibly be? Well, x always has to be between 1 and 3. We're going to assume that from now on. So that means that this could be no bigger than 6. So it's definitely going to be less than 6 times x minus 2. And now we can set this less than epsilon and divide that 6 to the other side. So now we'll set this less than epsilon, and this part right here is equivalent to saying that, to writing x minus 2 is less than epsilon over 6. So what we can conclude now is that, therefore, if you're given any number epsilon greater than 0, we should choose our delta to be, now it's not quite going to be epsilon over 6, it's actually going to be this. It's going to be the minimum of epsilon over 6 or 1. Why do we write it like this? Why is it the minimum of epsilon over 6 or 1? Well, if someone came along and gave you the number 12 for epsilon, then 12 divided by 6 is 2, of course. However, we wouldn't pick our delta to be 2 because we said we always assumed that delta was chosen less than or equal to 1. So if you were given delta to be 12, if you were given epsilon to be 12, you would choose delta to be 1 and not 2. So that's why we have to say it's the minimum of epsilon over 6 or 1. And that is our answer. And so there we go. So we've found that given any epsilon greater than 0, if we choose delta to be this quantity, then for x minus 2 in absolute value taken to be less than delta, that will imply that x plus 3 times x minus 2 would be less than epsilon. And that implies that f of x minus L is less than epsilon. Now, just notice one thing here. There's nothing sacred about choosing delta to be less than or equal to 1. We just choose 1 because it's a very convenient number. If we had chosen the number, let's say the number 2 right here, instead of 1, say delta is always less than or equal to 2, then this would have been a 2 right here. This, let me put it down here. This value right here, this 1 would have changed to a 2, in which case these values would have changed to 4 and 0, in which case x plus 3, that would have been less than 7. You see 4 plus 3 is 7 now. And this would have been epsilon over 7 instead of epsilon over 6. And our answer would have become the minimum of epsilon over 7 or 2. I just want to make sure that you understand what's going on here with choosing this delta less than or equal to 1 by supposing it's a value other than 1. So that's how everything would change. But we always pick delta to be less than or equal to 1 because it's such a convenient number. So when you're doing these problems, always pick it to be less than or equal to 1 when you're doing these quadratic limit problems. Now let's take a look at another example, and you can try this one on your own to make sure you understand the concept of how we do it. So try this one on your own. Prove that the limit as x approaches 4 of x squared minus 2x equals 8. Notice if we put 4 in for x here, we get 16 minus 8, and that is 8. So try this one. Assuming you've done that, I'm going to work through it here now. So we begin by looking at absolute value f of x minus L, and we're going to that's going to be equal to And now let's manipulate that. Let's see, that factors nicely as and notice right here, that part right there is our x minus c. So that we want to keep, right? That 4 right there comes from right up there. And this part we want to get rid of. We want to bound this by some number. So what we're going to do is we're going to say that from now on, we're always going to choose the delta to be less than or equal to 1, in which case x minus 4 will always be chosen to be less than 1, because we always pick this less than our delta. And that is the same as saying that x has to be within 1 unit of the number 4, so x can be between 5 and 3. So x is always going to be between 5 and 3 from now on. So now this part right here, we can rewrite that as, or we can bound the x plus 2 like this. So this is always going to be less than, let's see, we want to get rid of the x plus 2 term. Well, what's the biggest it could possibly be? Well, x is always between 3 and 5, so the biggest this could be is 7. So this is going to be less than 7 times x minus 4. And now we will set that less than epsilon. Now since this is a number, we can divide it to the other side, so this part right here is equivalent to saying that x minus 4 is less than epsilon divided by 7. And so now we have our answer. So therefore, if we're given epsilon greater than 0, we would choose our delta to be the minimum of epsilon divided by 7 or 1. And there we have found our delta. For any epsilon greater than 0, we can find a delta. So that f of x minus L is less than epsilon whenever x minus 4 is less than our delta. And this is how we would choose delta. So that concludes our discussion of using the Epsilon-Delta limit definition to prove limits involving quadratic functions.